Welcome, everybody. We didn't have time in lecture today to get through all of the coding style tips that I'd like to give you. So I'm going to do this offline lecture for you to view at your leisure. Okay, let's start with a basic example. So you look at this code, study that for a moment. What do you think? Is the style good? Not good? Hopefully you're thinking the style of this is terrible, because it is. It's missing basic punctuation, or the equivalent of punctuation for code. It's missing indenting. So we should be indenting 3 to 4 spaces for every level of control structure. So on the right, I've done that. It's much more obvious now what the structure of the code is. So be consistent in your indenting. And most of you will do that. What some people forget to do is vertical spacing. So break your code up into paragraphs. Don't be afraid to put some, a couple of blank lines between your functions, put blank lines between blocks of code. It makes it a lot easier to read. Okay, so use white space, make the structure of your code show through, both vertically and horizontally. Okay, so I'll give you 30 seconds or so to study this code, maybe a minute. So read through this and see if you can figure out what it does. Okay, so I'll give you can always pause this. I'll give you maybe 30 seconds, and you can pause it, take another 30 seconds or so for yourself. It's not extremely complicated. See if you can understand it. Okay, I actually gave you 40 seconds, so a little more there. Feel free to pause, ponder this for a bit more, see if you can figure it out. What I've done is with students in the class in past years, very few have been able to figure out what this function does. What about this version? So let's take another 30 seconds. Just read through this code, see if you can figure this one out. Okay, again, I gave you a little bit of extra time there. It's 40 seconds. You probably found this a lot easier to understand. Not sure if you fully grasped it or not, but it is much easier to read. And you probably, from the name, can figure out this is the definite integral. So you can see that it's going through, it's got a loop, it's starting at the left boundary, going to the right boundary, it's going up by step size, and it's getting some average y value and computing an integral. So you can get a lot more information out of this easily. And you may have figured out exactly what this did, or maybe you haven't figured that out yet. We'll go back here. This is the earlier code. It is structurally identical. The only thing that's changed are the variable names. And notice these variable names are not terrible. They're not misleading. They're just short. X, A, and B. A and B are commonly the bounds of an integral, right? So we're taking some function from A and B, and we're integrating it. And you might figure that out from this, but it might take some effort. And from this, it's pretty clear. You're computing a definite integral between x left and x right. And if you look carefully at this, you hopefully can figure out even what the function is. Function is 1 over x. Okay, so what's the point? Variable names matter a lot. I wrote a lot of code like this earlier in my career. I wrote electromagnetic field solvers, and this is often the way physics code is written. Just very short names, like you're translating mathematical equations into code. And it's much harder to read than most people think when they write it, including me. Use longer, more descriptive variable names than you might otherwise do it. It's going to help your reader a lot. Okay, so descriptive variable names. Couple of conventions that people commonly use. Underscores. to separate words. So you should have a lot of variable names that are more than one word long. If all your variable names are one word long, probably too short. Or use what's called camel case. Camel case separates words with uppercase letters. In C++, a common convention is that types start with capital letters. So if I define a new type, so I'm defining a class called my class here, and notice I start with a capital letter. And if I declare a variable, so this is declaring an object, not a new type, it starts with a lowercase letter. So that's a very common convention in C++ that I recommend you follow. All right, so this is the code you just looked at. We figured out it's a definite integral. It was much easier to read with these more descriptive names. Now let's just look at this version for a few seconds. So I'm going to give you 30 seconds to just read through that code. Okay, and that really was 30 seconds. This you probably found pretty easy because by commenting it, we've pretty much turned this into a literacy test. Our better variable names made it a lot easier to understand this, but now that we've commented it, almost anybody can get the big picture of what this does. So we've commented what the whole function does. Compute the definite integral of 1 over x. So what is the function? It's 1 over x between x left and x right. And there's a step size in here. We can change that. Smaller values will improve accuracy, but they'll increase computation time. So function level comments are very important. Every function you write should have a function level comment saying, what does it do? In addition, if you've got little bits of tricky code, you should comment them. So in this case, what if the distance between x left and x right is not evenly divisible by a step size? Well, we wind up with a little bit of our integral, right? We're integrating and we're integrating in all these little steps. Well, we find up with a little bit at the end that is a smaller step right here. And that's what this is handling. So we've got a little bit of tricky code to figure out what x2 should be. That's how far we're integrating on the x-axis. And it's mostly kind of obvious. x2 is just increment by the step size from the other side, x1. But at the very end, it might get a little more tricky. So we comment that. And both those kinds of comments are useful. Take 30 seconds to just read these comments that I just made up from pretend programs. So it is a file called asteroids.cpp. This comment says this file implements an asteroid AI. It maintains a current position and a velocity for every asteroid and ship, divides the screen into n bins, and computes the desirability of moving to each bin, and so on. Okay, so that's first comment. Second comment in a file called studentrecord.h. It's the main data structure used to store all information about a U of T student. It's a linked list. And then we have some comments on the various, so we've got a structure, we've got comments on each member of the structure. So how many classes are you in the current semester? How many classes have you completed and passed? And what's the next record in this linked list? And finally, I've got this comment. Compute the sum of the array over all of its elements. So I'm commenting what the loop below does, because that's exactly what this loop does. All right, so what do you think about these comments? Are they useful or not useful? Okay, so take a moment to make up your mind. Would you write all three of these comments? Do some of them seem more valuable than others? What's your opinion? Okay, got that hopefully gelled in your mind. Here's my opinion on that. The most important comments give the big picture. Okay, that's the hardest thing for someone reading your program to get. Why did you do this? How does this program fit together? They can get the details, but they have a lot of trouble reconstructing the big picture. Your documentation should be in your comments. So you could write a separate document that says, how does my program fit together? But the problem is that separate document usually gets lost, it gets out of date, it's not in the code, people forget about it. So sometimes you can have one very high level architecture document for a program and keep that up to date, and that's a good practice. But you probably aren't going to be able to have a whole bunch of different documents that are kept up to date. So as much as you can, put your documentation right in the code as comments. So in my opinion, the importance of comments increases as they become more big picture. So put comments at the top of your files. What is this file for? So maybe I've got a comment saying these functions are all grouped in this file because they're going to simulate a resistor network, and they're going to work, and we're going to proceed in the following stages. So that's my opinion, the most important comments. Next, and also very important, are class and data structure definitions. So if you can understand the data, what is this class for? What is every data member inside of it for? You can understand the program. You can understand how to modify it. If you do not understand its data, it's very hard to reason about it and to modify it. So comment that. Commenting at the top of a function. What does this function do? That's very important too. Not quite as important as the other two because it's a little easier to figure out, but you can help me not have to read the function. You can tell me what it does, and that may be enough information for me. And finally, comment tricky code like we just talked about. Not very useful, or sometimes not useful at all, are comments that translate C++ to English. So you don't want to write a comment that says loop over all elements of an array if you can immediately underneath it have a for loop that obviously loops over all elements of an array. That's not very useful. Go a little higher level. So on my previous slide, I would say, this comment, which is a high level, what's this whole file, whole algorithm about? That's the most important. This is quite important. This comment that says, how does this data structure work? What is this class for? And this comment isn't bad because it does tell me what 3 lines of code do. So it saves me a little bit of time, but it's not nearly as important because I can figure that out pretty quickly. Okay, take a look at this code. Again, let me give you, 30 seconds to just look at this code and think about it. Anything you don't like about this code, because there's something I don't like about it, something that will cost you style marks. Okay, so you've had your 30 seconds, and hopefully you saw this. It's using magic numbers. So numbers that we're not sure where they came from. They're just in the program. They're going to be hard for someone else to understand. So there's a magic number 20. Why do we have 20 weights? I don't know. It's not commented. If we have to change it from 20 weights, it's going to be a pain to find all the 20s. Okay, so yeah, if we were to change the size of this array, we've got, I can just see here already, we've got 2 places to change it in. And that's not good. That's a possible bug. And in a larger program, we might have a lot of places to change it. And maybe some of them wouldn't be 20. Maybe some of them might be 19 because we're going to go up to 1 less. That's challenging. We're also returning magic numbers. So our return codes from this function are all integers. And it's not clear what they mean. So sometimes from this function, we return -1. Sometimes we return 0. Sometimes we return 1. They must have some meaning, but it's not obvious. They're just integers. If I read through the code carefully enough, I can see, what's the logic by which I return these things? So maybe I can infer some meaning to them, but it's not very clear. Okay, so how can we rewrite this? We can use what are called named constants. And there are many ways to create named constants in C++. But basically, I've gotten rid of those magic numbers, and I've replaced them with, they're still constants, they're still numbers, but they've been given a name. Okay, so I've defined an integer, and I've said it's constant, meaning it will never change, called numWeights, and it's equal to 20. Okay, so I use that for my array size. And it's used now in 2 places. If I ever have to change the size of the array, I only change it in 1 spot. Change this number, and guaranteed all the code's going to be fixed up. So that's great. Here's another way you can make a constant. You can do what's called a preprocessor constant. So this syntax will also make me a number. Basically, during compilation, everywhere that this name, weight 0, occurs, this will be pasted in, 0. So another way to make a constant. And I use that. Um, Actually, I didn't use it in this particular code. I guess I'm just giving an example of you could use that as a way to make a constant. It is probably considered not quite as nice a way to make a constant as this first method or the method that I'm going to show you. The reason is it doesn't show up as nicely in a debugger. The weight 0 name kind of gets replaced during the compilation process, so it doesn't show up in the debugger as nicely. The other two methods, you'll still see the name like num weights when you're running the debugger. Okay, this third way to make named constants is called an enumerated type. So if I need to make a bunch of related constants, a nice way to make that is something called an enumerated type. You give the type a name. So I'm going to say this is a type called weight return. And I'm going to define a few related constants. I'm going to call one has neg, and I'm going to set that equal to -1. I'm going to call another has 0 and set that equal to 0, and another all pause and set that equal to 1. And these are really just integers. Enums are just nicknames for integers. So, but now I can refer to these names instead of referring to magic numbers of -1, 0, and 1. So you use this for groups of related integer constants. I could do it by just making a bunch of these kind of declarations, and that would work. But this is considered a little bit nicer because it groups them together. So what does my function check weights look like now? Well, I got rid of my magic number for the arrays, and my return types are now, I'm returning these enumerated constants. So I'm still returning from the point of view of the processor, I'm still returning -1, 0, and 1. It's all the same, right? Actually, you can return these integers. But when I'm reading the code, I see much nicer names. So if there's a weight that is less than 0 that I ever find, I return has neg. If there's a weight that is equal to 0, I return has 0. And if I get all the way through this loop, I didn't return from either of those, I return all pause. So now looking at this code, I can see I understand what each of these returns mean. Is there a negative number somewhere in this weights array? Is there a 0 somewhere in the weights array, or there isn't? They're all positive. It's made clear by giving names to these constants. Okay, so that's much better. Constants, it's nice in your code to be able to tell what's constant and what might change. There are two conventions that people use. So the one I used above is all caps. So you can use all capitals for constants that won't change while the program is running, or you can put the letter K in front of it. So K, my constant, would be another way to name these. So I might basically, put something like K num weights, and that would be a reasonable name for one of these constants if I wanted to use that other convention. Both of those are fine. Okay, so that was about don't use magic numbers, use short functions. Short functions are easier to reuse. They let you fix bugs in one place, not many. If you've basically made helper functions and called them all over the place, you instead of replicating code. They make your code easier to read by providing more abstraction. So the helper functions that you've created, they have names, they tell you what they do. Functions, think about how long the functions you write usually are. Okay, how long do you think they should be? They should be shorter than you think. You should have a lot of 5 to 10 line functions, and you should very rarely, maybe never, have a function that's more than 100 lines. And many people, myself included, sometimes violate these rules, but it's bad to violate them. We tend to just keep adding a few more lines to a function, just a few more, and not breaking it into smaller functions. It's better to try to keep your functions short. Okay, so look at this code. What do you notice about this code? I'll give you a few seconds to look at it. Okay, hopefully what you noticed is that this block of code and this block of code are identical, except we changed the variable we're working with. So we are computing the absolute value of every entry in this array A and then averaging them. And then we're doing the same thing here for B. So we've changed what the name of the array we're working with is, and we've changed the name of the variable that is our output. But that's it. Otherwise, the logic of this is identical. So that's not very good. We've got cut and paste coding. We've got duplicated code. Okay, so when you see this happens all the time. You realize, oh, this code is almost the same as this code. You refactor. You go, okay, that's not best practice. I should turn this into a function. So writing code isn't a linear process. You rewrite it to make it cleaner, to make it better, just like you write an essay in multiple drafts. Okay, so if we go and rewrite that, we're going to wind up with code like this. So let's go back here again. We had this function, and it basically had these two repeated blocks of code. What we're now going to have is we're going to write this helper function, call it compute absolute average, and it takes in an array, and it returns the average of the absolute value of all the entries in the array. And then in the function we had before, we would basically replace its body with just two calls to this absolute average routine. If I go back, you notice the code's not much shorter, right? So I had to make this helper function. I call it twice. It's not much shorter than when I just pasted two copies of those loops inside of this myfunc. But it is easier to understand, right? When I look at this myfunc, it's pretty obvious now what it's doing. I don't need to read the two loops to figure out what they're doing. I can just read this name, compute absolute average. And maybe I should use an even longer name. Maybe I should actually say compute absolute average, so it's even more obvious to the reader. It's clear I'm doing it twice. So, and if I put a comment, as I should, above this function about what this does, compute the absolute ... gets even easier to understand. This is also more maintainable. There's less chance of someone copying the code in the future. So we had two copies before, but as the code ages, there might become more and more and more copies. Now we've just got a helper function. There'll just be more calls to the helper function. So it's going to make our code shorter and easier to understand in the future as well. Okay, so take a look at this code, which is talking to the Streets Database API that you're using in Milestone 1. So I want to get the name of an intersection, and I'm actually going to start with some start intersection. I want to turn that into a street segment, and from that, I'm looking at the two elements in that, and then I'm getting the street segment info of that, then looking at the two element of that, which is another intersection, and I'm saying get the intersection name. So I'm trying to do too much on one line, right? To kind of unpack what is going on in this function call, because it's a function call of function calls, and I'm accessing data members that came back. It's hard to understand. I mean, I got confused as I was reading through it there. So that's too much on one line. Break it into multiple lines, use some well-named temporary variables, show your work, and it's easier to understand what's going on. So this exact same functionality I can do by saying, okay, I've got some starting intersection, and I want to get the first street segment that comes out of it, okay? From that street segment, I want to get what it goes to. That's this line. Get me this destination intersection. And from that destination intersection, I want to get the name. Okay, so this is where I started with my start inter. And I want to get this name. May still not, I had to still read through that, draw myself a little picture. But the fact that I have these temporary variables showing me step by step what I'm doing, this is easier to understand. Okay, so don't try to do too much in one line. Show your work. As we talked about in the tutorial, this also makes it easier to debug your code, because when you're running the debugger, I can actually hover my cursor over each one of these variables and see what it is. So I can see this partially completed work as it happens to. Okay, seventh tip is group related data into classes. So on Milestone 1, you're going to have a bunch of global variables to try to make your functions fast enough. And you could make all of those data structures. So here I've got a bunch of vectors to store various things that I think are going to be useful to me. You could store each of them in a separate variable, separate object. So I've got a bunch of different vectors with different names here. Now, these are global vectors. So I've kind of polluted my namespace. These variable names can be accessed from anywhere. If I instead group them inside of a class, okay, so I make a class, I'll call it segment data, and I put all of the same information in as members inside this class, then I make one global variable. So a global variable, which is still a vector, uh, but each element of the vector stores all of this information grouped together. That up here was in 4 separate vectors. It's easier to understand. Okay, I've grouped related variables together. There's less namespace pollution, and it's more obvious that this structurally I can look at this and say, oh, okay, this is an important global variable. It's got all these things together. Less obvious when I just have a whole bunch of global variables. And again, I should be commenting what are these things. Okay, so in real code, I would put more comments in. If this is a global variable, it's important. I should have comments saying exactly what is this thing? What are all of these data members inside of it? Okay, look at this code for, you looked at this before. I told you what this check weights function should do. It's supposed to return has neg or has 0 or all positive. Okay, and read through this code and see if you see anything wrong with it. I'll give you a few seconds. I'll give you 20 seconds or so. Does anything look funny about this? Okay, I'm being pretty subtle. There's something funny here, but it doesn't jump out. I'll give you the test case. So I test this program, and I actually find that it fails one of my tests. And here's the test that fails. I send in this weight array with entries of values of -1, 2, 3, 4, 5, 6, up to 20. Okay, so the first entry is negative, all the other ones are positive. So looking at this code, what should happen is I go through this loop, and every time I go through this loop, I check is there a 0, and if there is, I return have 0. And I check is there anything less than 0, and if there is, I return has neg. Well, the first element right here is negative, so I should obviously return has neg. But it doesn't. When I run this, it actually returns all pos. So that seems kind of baffling. And you may stare at this code for a while going, it doesn't make any sense. It's just a for loop and some if statements. It's obvious that it should not return this. For this case, it shouldn't have returned that. It should have returned has neg. Okay, and you might stare at this for quite a while trying to find the bug. If you pay attention to compiler warnings, and you have to turn them on. So when you compile with G++, you can ask for more warnings. So WAll means give me all the reasonable warnings. And we've done that in the make files we've given you for your milestones. So this is already on. You don't have to do anything. Warnings are basically the compiler saying, well, I can interpret your code, I can compile it, I can turn it into a program, but there are things in it that look unusual, right? So I can still tell what you want me to do and make you a program, but you should think about whether this is the program you really want because you're using some unusual constructs. So in this program, the compiler will give you a warning saying, in function check weights, line 11, there's a warning, suggest parentheses around assignment used as truth value. Okay, so that sounds a little cryptic. But let's go look at line 11. And this is line 11. So that's the first thing this warning told us is go look at line 11 in this function. There's something funny about it. And assignment used as truth value means you're not actually doing an equality test. You're not using the equal operator. You have used the assignment operator. And this is legal C++. But what this does is it actually sets weights of I equal to 0. So remember we had weights of I was -1, 2, 3, 4. Well, not after we go through this loop. First time we go through this loop, this changes to 0. So that's what we've got, 3, 4, and so on. And that is going to result in not returning has zero. Okay, so we're not going to, that's going to evaluate to false. We are not going to return has zero. All the other entries are positive, so we're going to return all pos. This is very subtle because you know that you wanted to write this equal equal. So your eye kind of fills it in. You know, you're looking at the code and you just see equal equal because it's obvious that you were trying to do the equality operator, but you didn't. So this warning can save you a lot of time. And there are many other useful warnings. They're telling you this code looks dodgy and you should get rid of those warnings. Okay, now some warnings that you can look at the code and go, yeah, there's nothing wrong. That is what I mean, it's fine. The problem if you leave those warnings in your code is that your partner, you add more code constructs that cause warnings and you don't see those warnings. You don't see them because you rapidly get to a point where you've got 5, 10, 20 warnings and you went and looked at them and they were all harmless, but now the 21st warning comes in and that one's actually a bad one. But you don't see it because there's just a pile of warnings going by. So if you want to pay attention to warnings, you have to stay at 0 warnings. And that's what most high quality industrial code does. We had a rule that I created when I was at Altera of we had to be 0 warnings, warnings clean in Quartus, which was 17 million lines of code by the time I left. So if we let a lot of warnings creep in, you're never going to be able to pay any attention to them. You can only pay attention to warnings if you have none and you notice when the first one comes in. So you got to fix them all. You got to stay at 0. And as I said, we've already turned on all the warnings that we consider useful in your makefile, so you're going to get a bunch of warnings if you do anything the compiler considers dodgy. And to teach you to not have warnings in your code, this is one of the things we'll look at in your style mark. EC 297 submit actually tells you, do you have warnings in your code or not, in case you didn't notice, because it's immediately going to cost you some marks. So just get rid of them. Okay, so you don't have to do this, but this is a useful technique that you can use. But as I say, we will not be assigning style marks for this. Your TA will be impressed if you do it, so it can raise your style mark, but it won't reduce your style mark. So you can use something called assertions to verify assumptions in your code. And this is an example of what's called defensive coding. It's try to think of things that could go wrong and put checks in for them. So let's say I have a function and it takes in a pointer. And I could put a comment in saying, don't ever call this function with a null pointer. Okay, that's kind of helpful. Tells people don't do that. I didn't handle that case. And then we've gone and dereferenced this pointer and checked if what it points to is equal to 1. Okay, so this is not going to work if the pointer's null. If the pointer's null, this is going to crash. Okay, so it will crash with null. So it's good we put this comment in. But we can do better. Okay, so instead of just putting a comment in, we can include a header file called assert.h. And now we can use a macro, so it's like a function, but implemented a little bit differently, called assert. And what assert takes is just in brackets, you put a logical condition. And that logical condition has to evaluate to true for the program to keep going. So my logical condition I put in is the pointer must not be null. If the pointer is not null, this assert does nothing. The program just keeps running, goes right through it. If the pointer ever is null, this assert will stop the program and print an error message. Okay, so if we send in a null pointer, this assert's condition is false. It'll stop the program, and it's going to print out this. It's going to print assert failed at line 208 of file myfunc.cpp, pointer not equal to null. So it's better than a comment because someone reading this, I mean, you could put a comment if you want as well, but someone reading this can see, oh, the pointer had better not be null. And I'm not just telling you don't do that. I'm actually checking it whenever this function is called. Okay, so you might wonder, well, we've got speed tests. Does that assert take any time? It doesn't take much time, but it does take a little bit. If you're worried about that, you need to get the last little bit of speed when you submit. You can, at the top of your file, before you include assert.h, you define, okay, so this is a command to the C preprocessor, this kind of text processing tool that runs before the main compiler. So we define something called ndebug, not debug. And if you define this before assert.h, it basically turns off assertion checking. So now what will happen is this assert won't do anything as long as this line is active. But if I want to turn assertion checking back on, I just have to comment it out. All right, so this allows me to turn off my asserts in a file, get back any little bit of speed I want before I submit my final code. But I can, comment out that line, that define debug, and I can turn back on this extra checking when I'm debugging. Other kinds of defensive coding. So when you delete a pointer, C++ just leaves whatever the old value of that pointer was, it leaves in the pointer. So if you forget you've deleted it, you might try to use it again. And if you immediately instead set it to null right after you delete it, then if you try to use it, you'll immediately crash. And that's helpful. That's going to help you find, oh, I actually deleted this pointer. It's not pointing at anything. I'd rather crash right away. So now if I use this pointer and I try to dereference it to get at some value, if I have this line where I set it to null right after I deleted it, I will for sure crash. If I didn't do this, if I said if I didn't have this line, I might crash because it's not valid, but I might not crash because we just don't know what's inside this pointer variable. If I ran valgrind or debug check, it should tell me this is bad, but I might not be doing that all the time. So this little bit of extra code makes me a little more safe. A more advanced technique that you're probably not going to use in this project, but is useful to know about, is you can write self-checking code. And I do this a lot in my programs. So I'll write functions like, for example, validate key data structure, and I'll pass in some data structure. So if I know certain properties, for example, working with graphs, and there are certain properties that graphs have to satisfy, I could write a function that just makes sure that the graph I'm working with satisfies, all the nodes have some edges. If that's what I think is one of my invariants, I could write this check to make sure that's always true. And therefore, if I mess up my data structures, this checker can say, well, your data structures don't really make sense, right? They're not consistent, or they violate some of the things that you said they'd always match. Now, again, you're probably not going to do that in this course, but it's a generally useful technique in more complicated programs. This is a funny example I saw on the web of, they should have used assertive validity checkers. This is a program that you can type in on the web something that you want printed on a cake, and someone wanted to wish their Aunt Elsa a happy birthday, but clearly used some special characters. So maybe Elsa's native language is not English, and those special characters led to a bug, and basically all sorts of HTML error messages were printed out on the cake. If they had an assert or some kind of validity checker, maybe they would have caught this, and Elsa would have been less confused. So sometimes it's better for the program to, stop running because it's detected there's a fault than to just keep going and generate invalid output. Okay, so that's it for style tips. The key to maintainable code is first your mindset. Code is going to be read more than written. You're going to read it to modify it. Other people are going to read it. In this course, your teammates are going to read it. In your career, you're going to write code that may live on for a very long time, and people in your company or colleagues around the world might read it. So code is much harder to read if you're not the author, or even if you are the author, but it's been a while since you wrote it, than you think. So you have to work to make it readable. Similarly, it's going to be modified a lot. Code tends to be a living thing. So make small functions, avoid repeated code, because that makes it easier to modify your program. Keep the tests with the code. Now, we talked about that earlier. That wasn't in the style guide, but we want tests that, unit tests that go along with the code. We want the documentation to be in the code. So comment the code, because that's the documentation that's going to survive. We didn't talk about this, but code reviews are really useful for developing a good code style and making sure that you and your colleagues can read each other's code. So in this project, this is a great opportunity for you to read the code of your teammates and vice versa, discuss, can you understand it? What can the person change to make it more understandable? and so on. So you really learn what's readable by reading other people's code and seeing how difficult it is, and by getting feedback from them on what they understand and don't understand about your code. I've used Google as an example of a lot of best practices in software. And Google, their revision control system, so what they use, their internal system, which is not Git, but has Git-like features, they will not make changes visible, so not fully committed until they've been reviewed and approved by at least two people, actually. So one person who's an expert in the system you're working in, like what is that system trying to do, and another person who is has basically been senior enough that they understand the Google code style, so that person can review the code for style. And the last thing I'll mention is I've posted a rubric with milestone 1 on project management, code style, Git usage, wiki, that gives you some concrete things that your TA is going to be looking for in your code and in your project management. So take a look at that rubric, and it kind of distills down a bunch of the things that I talked about in the lecture today into a checklist, basically, that your TA is going to be using. So it's useful for you to know what is that checklist. And that is everything. Good luck writing readable, stylistically beautiful code.